Hi everyone, welcome to week 9 of Astronomy 236. This week we're going to start talking about exoplanets. I'm particularly excited today because exoplanets are the topic that I actually spend my time researching. So I'm really excited to share a little bit about what I know about these exciting new objects with you this week. So I wanted to start off just by reminding you that for thousands of years, we only knew about a handful of planets in our universe, and those were the ones in our solar system. We knew about them since the time of the Greeks, when it was clear that they moved differently from the other stars in the sky. And over the years, we studied them and we learned about them, and we learned about their moons, we learned about their masses, and we learned about what they're made of. But we were always curious, can these be the only way that planets can be? Are there other stars out there that have planets like the ones in our own solar system? Are the planets out there similar to the ones that we have, or are they different, or are they more diverse, or are they more unique? And until recently, we really had no way of answering these questions. So, one of the reasons for this is that finding exoplanets is hard. So, what are some of the ways that we might go about doing that? The most obvious one involves taking a picture of another star and then looking very close to it to see if there are any dots that look like planets that are orbiting that star. We call this direct imaging. And this is indeed a way that we can find exoplanets. We'll learn about this later in the course. But it's quite difficult technically, and I'll explain to you why that is. And the basic reason is that planets are faint, stars are bright. So, to put it into context, looking for an Earth sized planet right near a star like the Sun from a distance of maybe 10 or 30 light years away is about the same challenge as looking for a firefly flying next to a lighthouse about a meter away from a lighthouse and being able to see that firefly from a distance of about across the country from Los Angeles to New York City. So this is extremely difficult technically. And for that reason, directly imaging planets, actually taking pictures of them, was not the first way that we were able to start learning about planets outside of our own solar system. Another thing that makes this challenging, and we'll come back to this problem repeatedly throughout this course, is that Earth's atmosphere makes things really difficult. So if you look at a star from the Earth, this is what it looks like if you zoom in really closely. The star appears to be moving around, jiggling around. We actually all know about this. This is what is causing the twinkling of stars that you see in the night sky. It's pockets of air in the Earth's atmosphere that are moving around, turbulent, due to winds at high altitudes, pockets of slightly warmer, slightly cool air that bend the light and cause it to jitter around like this. So this twinkling, this effect, makes it really, really hard to see a very faint object right next to this star right here, even within that region of where the star is blurred out by the atmosphere. Here's another example of what the atmosphere does to images. This is a close-up of some craters on the moon. And you can see that if you take exposures, take images really rapidly in succession, you can see that this picture is getting distorted. That's due to all of these pockets of air turbulent up in the upper atmosphere, moving around with different temperatures and different pressures and causing light in slightly different paths to bend in slightly different ways. So you can imagine how difficult it would be to look for something incredibly faint, incredibly next to a much brighter star when everything is moving around like this. So this is why direct imaging is not one of the first ways that we use to find planets. Instead, we use indirect methods to find planets. We don't look for the planets themselves, we look for the impacts that they make on their stars. And traditionally, historically, the most successful way early on was using the Doppler effect. We've talked about the Doppler effect in this class before. We can use it to measure the velocity of stars or galaxies towards or away from us. We're doing exactly that here, except now instead of looking for a velocity once, kind of like Hubble did when he was measuring the velocities of galaxies, we want to look for velocities many different times to see if those velocities are staying constant or if they're changing a little bit. And if these velocities are changing a little bit, we can infer that perhaps the reason they're changing is because the star is getting tugged very slightly towards us and very slightly away from us over time. And that tug can be due to something orbiting it. So here's an example of what happens. Here is a star. Here is a planet, or maybe even another star. It doesn't really matter here. But the stars will orbit each other. That's because even though the star is much more massive than this companion, the companion still tugs on the star and causes it to move in an orbit that's equal and opposite, essentially, to its own. This is just Newton's laws of mechanics from classical mechanics. One force in one direction has to be equaled by another force in the other direction. So this equal and opposite reaction of forces causes the planets to dance around. First, I want you to take a note of the size of this orbit. So I put this ruler up here, and to note that this star here is basically moving back and forth the length of this ruler. This will be important in a bit. So these stars are going to start doing their dance now, or the star and this planet. And as it happens, they move in opposite directions, and they're always staying opposite from each other in their orbits. And they continue like this. And as we observe from our telescopes over here, we can see the spectral lines from the star moving back and forth slightly due to the Doppler effect from the motion caused by this companion. And we see it repeating over and over again. So this is great. This is a good way for us to find if there's something orbiting a star, even if we can't see it. All we have to do is look at the star itself and see if it seems to be moving in a way that would suggest that. But there's a catch. And the catch is, what if things aren't lined up quite this way? What if instead things are lined up away from our line of sight so that the motion is mostly away from this direction in which we measure Doppler shifts? Remember, we only measure Doppler shifts away from us and towards us. Doppler shifts don't really do anything if they're moving parallel to the plane of the sky or perpendicular to our point of view. In the previous example, we were looking at a system where the star and its companion were orbiting in the line of sight of our observations. Our observations are pointed this direction, and we see everything lined up nicely. That means that the entire motion we see of the star back and forth is in the direction of our line of sight. So we see this as a Doppler shift. But what if our line of sight is tilted with respect to the motion of the star? So in this case, I have two stars orbiting each other. This motion, therefore, this tugging by one star upon the other is going to be much larger than it would be for a planet. But we still measure the same tug because this star here is going to move the same distance in our line of sight in the direction of our observations as it did in the previous example. So if you don't really understand what I mean by that, here's a way to look at it. So here's this ruler, the same ruler that I had in this previous example. But now I've lined it up so that it goes from the very bottom of this orbit here to the very top over here where this star goes. And as you can see, the orbit is in that same length. It moves the star moves the same distance back and forth in our line of sight as it did in the previous example. But now it just happens to have a lot more motion outside of the plane, outside of our line of sight as it did before. So the star is really moving a lot now, but we still see the same amount of motion and therefore the same speed with our Doppler observations. So it's impossible to distinguish small objects that are only tugging on their stars a little bit from bigger objects that are tugging on their stars a lot, but just happen to be misaligned with our line of sight. Now, you might be wondering, okay, well, why don't we just look at our observations and see if the star seems to be moving back and forth in the sky, because that's the direction it's going. And the answer is that's exactly right. That's something we could do. But it turns out it's really hard to do this, especially because of our atmosphere. So you can see that the atmosphere is jiggling the star back and forth. How could we ever tell if this jiggling is due to the star actually moving because it's being tugged by another star, or just a quirk of our atmosphere? So in general, with radial velocities, with this Doppler method, we can only measure the minimum mass. We know that if we see a shift of this size, it could either be due to a planet orbiting with an orbit along our line of sight, or it could be due to a star with an orbit inclined away from us. So this is what we call the radial velocity method. Radial velocity, just because we're measuring velocities, measuring speeds towards and away from us along our line of sight, therefore the radial motion. If you draw a sphere and we're at the center, we're moving along the radius of that sphere. And when you make these Doppler measurements over and over and over, sometimes you will see a pattern like this emerge, in which the radial velocity starts out at close to zero, then it decreases, then it increases again even further, and then it comes back. And it repeats this pattern over and over and over as this object orbits around. This is how the first exoplanet candidates were found. So the next thing I want to talk to you about is how large are these signals? How fast do planets actually tug on their stars? And to start off, I will give you an example of two stars orbiting each other, two of the most famous stars in the sky, Alpha Centauri A and Alpha Centauri B. Here they are right here. These two stars are orbiting each other, and we can measure the velocity of both of these stars in the radial direction. Here's what those observations look like. This is a long historical time series because we've been observing Alpha Centauri A and B forever. They're some of the brightest stars in the sky, and it's the closest system of stars to our own sun in the sky. So over time, you can see that the radial velocity of the stars changed. It went up and then it came back down. And now it's returning back up again for Alpha Centauri A. Alpha Centauri B is doing exactly the opposite, because Alpha Centauri B is moving, it's tugging the opposite direction. So again, this equal and opposite tugs is what's causing this motion and causing these stars both to orbit around each other. So the amplitude of this motion, the size of this signal, how fast these stars are going, is about 7 kilometers per second at the most that we can see it. So to put that into context, 7 kilometers per second is about the speed of the space shuttle flying around Earth when it's in orbit. So really, really fast, faster than a speeding bullet, literally. Planets, on the other hand, are much lower mass. So here's a handy diagram to show you what the masses of different objects are. We know about stars. These have masses that are typically about 80 times the size of the mass of Jupiter. And stars are objects that are big enough and massive enough to turn on nuclear fusion in their cores. Lower mass than stars, we have brown dwarfs. These are sometimes called failed stars because they're almost like stars in every way, except that they were never massive enough to really start to fuse hydrogen. But they do sometimes fuse a little bit of deuterium, hydrogen, with a second neutron in addition to its proton in this nucleus into helium. So brown dwarfs are kind of in between stars and planets. And then planets are lower mass than that. Formally, this definition is that anything that does not fuse deuterium is a planet. But to be fair, or to be honest, astronomers tend to not necessarily pay too much attention to that. It's still a matter of debate what the biggest planet possibly could be, or the most massive planet possibly could be. And this 13 Jupiter mass boundary is probably more something that humans have come up with than something that's really happening truly in planets and stars in the galaxy. So if we imagine that planets are much, much lighter weight, they're much, much less mass than stars, then probably they're going to tug much less on their host stars. And therefore, the tugging that they produce is going to be much slower and much harder for us to detect. And indeed, this is true. If we plug into classical mechanics, how big or how massive Jupiter is and how quickly it orbits around the sun, we can calculate that it should move our sun back and forth by about 12.4 meters per second, which is 27 miles per hour. So suddenly you've gotten this huge decrease in speed from kilometers per second for a star orbiting another star to a speed that we're very familiar with here on Earth, the speed of a car going leisurely down a small road. Planets are hard to find. And this is the biggest planet in our solar system. It only gets harder from there. Saturn, on the other hand, has a 2.8 meter per second amplitude, which is about the speed of a jogger. Earth is really hard. Earth only tugs our sun by about 9 centimeters per second, which is about the speed of a box turtle. And Mercury tugs our sun by only about the speed of a snail. So these signals are extremely small, and we have to be extremely precise in our measurements. Now, I want you to look back at this plot again, and I want you to notice something, though, something hopeful, which is that over time, our measurements have gotten much less noisy. So take a look at these measurements back from the very beginning of the 20th century. There are lots and lots of observations, and they are pretty scattered. There's a big scatter in all of these measurements. But over time, the scatter has gotten smaller. So take a look at these last few decades of observations. All of the observations go straight through this line, this best fit orbit that we've calculated. Then the reason is that over the last century, our technology has improved in leaps and bounds. And we've gone from making these relatively crude measurements over here to extremely precise measurements, which have enabled the detection of smaller and smaller signals with the Doppler method, with radial velocities. The reason we have this extreme improvement from the early 1900s to the late 1900s and the 2000s is largely driven by the fact that we astronomers used to do everything with photographic plates. So back in the day, images, pictures were all taken by coating a piece of paper or a piece of glass with some sort of film. And if that film has light that touches it, chemical reactions take place and they blot out that light. So these photographic plates record where light hits them. And this is how we took images of the sky, and this is how we measured the spectra of stars, by looking at the light that touched these photographic plates. And this caused a lot of inconveniences in astronomy. So this fellow here is at the Palomar Hale telescope. This was the largest telescope in the world in the 1950s, and it was the largest telescope in the world for decades after that. And what he's got here is he's got a photographic plate that he's going to put into the path of the light of this telescope, right into this little box here. Now, this is a big telescope. To do this, he has to be at the very top of it. So here's an image of that telescope. That guy is flying around up top here. If the telescope needs to point over this way, he moves over this way. So it's not an easy way to do astronomy. To give you a sense of scale, this is that same telescope with a bunch of people nearby. So he's really way up there, flying around 100 feet above the ground. The big change in astronomy came with the introduction of electronic ways to measure light instead of using these photographic plates. This has really been the biggest revolution. So now, instead of this guy having to fly up top of the telescope all night long in the cold, in the wind, trying not to fall out, trying not to fall asleep, he gets to sit in a comfortable room, warm, indoors with the lights on, and essentially click a button on a computer that tells a digital camera to measure the amount of light that's coming into the telescope. And to boot, this made it much easier to get the data into a computer, and it made it much easier for us to actually analyze that data. So this revolution is largely what drove the improvement in our measurement accuracy in the late 1900s and the late 20th century. So when we were able to finally start making these really good measurements of the velocities of stars, we started to look for planets. And this was really starting to take off in the 1980s. And the very first planet candidates that we knew about were announced in the late 1980s. So here's probably the first good planet candidate. It was announced by a group of Canadian astronomers, Bruce Campbell, Gordon Walker, and a collaborator named Yang. I forget his first name at the moment. And what they were doing was they were measuring these radial velocities for a large number of stars, and they were searching for any signals that could possibly be there. And what they found in this paper from 1988 was a weak signal here around a star called Gamma Cephei. This is what they saw. They saw that the star appeared to be moving towards us and then away from us, and then towards us and then away from us every 2.5 years or so. Now, this data is pretty noisy. It would be a long shot to say that this data proves that there must be a planet around the star. They kept observing, though, and they took another look in 1992. By this time, they had taken a lot more observations, so they were starting to see that it really does seem like this star is moving back and forth every 2.5 years. What could be the cause of this, though? Being very careful scientists, they went and they also checked how other things about the star were changing. And in particular, they noticed that the magnetic field of the star seemed to be changing strength every 2.5 years as well. That's what this graph is showing. So because it would be a very strange coincidence for the magnetic field of a star to be changing every time a planet orbited around it, they concluded this probably was not a planet. In fact, it was probably something to do with the star. Later on, however, about 10 years after that, in 2003, another group of astronomers finally did decide that this probably was a planet. They took more observations over a decade, and they continued to see this 2.5 year signal, this 2.5 year movement back and forth of the star Gamma Cephei. And they broke up their data into multiple different chunks, and they always saw that this movement looked consistent. And then the kicker was that when they looked at the magnetic field strength over the entire decades of observations, they no longer saw the pattern that had caused the Canadian team to be very cautious and to eventually conclude that this was not due to a planet. So in 2003, it finally became clear that this may have indeed been the very first planet that was discovered, but the team didn't get credit for it like they could have, even because they didn't originally believe in their results and didn't really claim them to be true. So the next year, 1989, we've gone back in time again, there was another discovery. This one was a lot more solid, and the question was not necessarily whether or not this object was there. There was pretty clearly a change in the radial velocity over time. There was pretty clearly something orbiting the star tugging it. But the question here was, what was this companion? So incidentally, this was discovered by my thesis advisor, Dave Latham, and we'll have a reading about how he made this discovery and how this collaboration came to be this week. And what they concluded was that this object that was causing the star HD 114762 to move back and forth every 84 days probably was too massive to be a planet. So you can see in the title of their paper, they call it a probable brown dwarf. And they calculated the minimum mass of this planet is about 11 times the mass of Jupiter. Now, you remember earlier I mentioned that the typical mass at which we cut off planets and brown dwarfs is about 13 Jupiter masses. So technically, this could be a planet if we believe that this limit here is firm. So in the abstract of this paper, Latham et al. Eventually did say that this leads to the suggestion that the companion may even be a giant planet. But they were cautious still. And they said, however, because the inclination of the orbit is unknown, the mass could be considerably larger. So they were worried that they had indeed detected this radial velocity signal, but they were seeing a star orbiting another star that just happened to be inclined away from our line of sight to cause it to look like the signal was small, even though the mass of the companion was large. Eventually, we will be able to resolve this question once and for all. What is the true mass of this star by measuring the side-to-side motion of that star on the sky using data from the Gaia spacecraft, which we've talked about a few times earlier. But until then, the nature of that companion, whether it's a giant planet, a brown dwarf, or even a very low mass star, is still up for debate. Finally, however, the floodgates really burst open after the discovery of a planet candidate around 51 Pegasi b. So this was done by a group of Swiss astronomers, Michel Mayor and Didier Queloz, and they found that there was a planet with a minimum mass of about half of one Jupiter mass, orbiting the star 51 Pegasi b every 4.2 days. They wrote this paper up. They called it a Jupiter mass companion, even though, recall, we don't actually know the inclination of this planet. We only know what its minimum mass is. And they published it. And this was the discovery that really set off the torrent of exoplanet discoveries that we've seen in the last few decades. And this is the one that's really given credit for starting the field. And this is the one that got the Nobel Prize. Now, one quick reminder before we end this lecture bite. When we were talking about looking for patterns in our solar system, one of the most important things that we saw was that the planets seemed to be grouped based on their mass. The rocky planets all seemed to be close to the sun, and the gas giants all seemed to be far away. And we believe that this was likely because the gas giants forming out here have more material. They have these, they're beyond the snow line, so they have ice that can help build up big cores and eventually scoop up all of the gas in the systems. These rocky planets down here never had the opportunity to do that. So it made sense that we would have small planets close to the star and large planets far away from the star. But our very first exoplanet, the very first planet that we discovered that seemed to set off the field that really convinced people that there were other planets around other stars, was a giant planet orbiting way inside the orbit of Mercury. This was a harbinger of things to come. Exoplanets have consistently subverted our expectations of what we thought was true in the solar system, and it's caused us to rethink a lot about what we know about the way planets form and evolve and migrate. We think that our basic idea that I talked about last week is generally still right, but we've had to add a lot of embellishments and complicate the theory and build it out significantly to keep being able to explain all of the amazing things we've seen around other stars.